All right. We're glad you're here, Greta. And our other mystery guest. We're glad that you're here too. All right, let's get started. We're going to dive into 5-1. I know that we have not much time left. It's almost Christmas time, right? Almost December. But chapter 5 is a pretty quick section. And the good news is, as we chuck through it, I think you're either going to have a very short quiz or your homework is going to count as your test grade. So that's a good thing, right? Yeah. All right. So let's go ahead and get started. So 5-1 is only one page of notes. So it's a pretty easy, let's just kind of get right in there and talk about some things. So we just spent a lot of time talking about triangles. And guess what? We get to spend more time talking about triangles. So all the things that you're learning in 5-4, guess what? You get to keep learning in 5-5. And sorry, I think I just said that wrong. All the things that you learned in chapter 4, they still apply in chapter 5. So don't just learn chapter 4 to learn chapter 4, learn it to learn it, which you should be learning everything to learn it. But, you know, in case you're like, I'm just going to get through this, it's actually important for chapter 5 too. So they kind of connect together, if that makes sense. Okay, so we are going to talk about something called the mid-segment of a triangle. Okay, so who remembers what a midpoint of a line is? You should be able to figure out just by the word midpoint. Midpoint. It's a point, yes, in the middle. Wow, there you go. It's a point in the middle. The midpoint of a line. Okay, so if I draw a line, the midpoint, if I can draw it correctly, would be the point that is in the middle. Okay, we're going to talk about something called the mid-segment of a triangle. Okay, and the mid-segment of a triangle, let's see how my typing skills are. The mid-segment of a triangle is a segment that connects the midpoint of two sides of the triangle. And I will fix this so you can actually read it. Ta-da! Triangle. I forgot a letter in there. A segment that connects the midpoints of two sides of the triangle. Okay, so if you have, pick a triangle, any triangle. Oh, we'll even use our shape tool to draw a triangle, so it'll be nice and pretty. Okay, so I have a triangle. Okay, if I go to my triangle and I look at this line, now I'm just drawing triangles over triangles. If I go to the triangle and I look at this line and I find the midpoint, the middle of it, okay, and then I go to this side of my triangle and I find the middle of it, and then I connect these 2 points, voila, this is the mid-segment of the triangle. Okay, if you kind of draw, that's very Christmas themed too, right? Let's draw a little bit more complex triangle. So it doesn't have to be a perfect, you know, isosceles triangle. The middle of this triangle is right here, or this in the middle of this leg is here. The middle of this leg is right here. So the midpoint of this triangle, or the mid segment of this triangle, will be right here. And it doesn't always have to be vertical. You could also draw the mid segment this way, right? The middle of this leg is here. I'm trying to do a different color. Middle of this leg is here. The middle of this leg is here. So this is another mid segment of the triangle. If my drawing is just amazing right there, right? Okay, first up, we get a theorem that has to do with mid segments of triangles. Because we're all hoping for a theorem first thing in the morning, right? Okay. The segment connecting the midpoints of two triangles, the two sides of a triangle, is parallel to the third side and is 1/2 as long, or is half as long as that side. So we just got a whole bunch of information in our first theorem of the day. All right, so here we go. The segment connecting the midpoints of two sides of a triangle is parallel to the third side and is half as long as this side. So this is a really important theorem. I'm going to give you like 1 minute to write this down in on your theorem sheet, because this is really important. Then we'll talk about what that means. All right, 1 minute, grab out your sheets, go. Okay, you guys all getting it written down? Okay, so this is actually awesome. I see a thumbs up on there. Awesome. Actually a pretty cool theorem. I mean, you know, all the theorems are awesome, so I couldn't pick my favorite. However, it's pretty cool in the terms of triangle because it gives you a bunch of things, a bunch of information about a triangle, and then we know a lot of things about parallel lines and so forth. So you'll see this little picture on here. Basically, when you draw the midpoint, or I keep saying midpoint. When you draw the mid segment of a triangle, the first benefit that you get is that you know that because it's the midpoint, so I'm working on my Christmas tree picture here. Yeah. Because it's the midpoint, you know that this line and this line are congruent to each other. And you also know that this line over here and this line over here are congruent. And that's just because we said that the mid segment connects the midpoints. And since this green line represents the midpoints, then the two legs get divided into two congruent segments. So that's the first thing we know. And then the theorem adds on top of that, not only that, but the mid segment, this line here, is parallel to this line down here. Okay, so why is that interesting that they're parallel to each other? Well, we just spent a whole lot of time in chapter 3, so hopefully that didn't all go out of your brain. In chapter 3, talking about parallel lines and when they're cut by a transversal, we are able to, you know, talk about the alternate interior angles and consecutive angles and all those types of things. So that's exciting. We've got parallel lines going on, right? And then the last thing we know, and this is also pretty cool, is if this, for example, is 10 units long, then the mid segment is always half of that. So the mid segment is 5 units long. So this theorem is actually pretty powerful, and it lets us learn about a lot about triangles and to be able to prove a lot of things about triangles. You guys are all thrilled, right? So excited. So excited you can't even chat. All right, good. Somebody's still there. Oh, there I see some emojis popping up. Okay, good. All right, so example 1, use the mid-segment theorem to find the lengths. All right, this will be a really cool window if it was a window somewhere. A large triangular window is segmented as shown. This is probably like some really cool triangular stained glass something, okay? All right, in the diagram, DF and EF are mid segments of triangle ABC. So we know that DF and EF are mid segments. Find DF and AB. All right, so this should be pretty easy peasy. Let's just do a little color coordination here. Let's make it a little bigger. Really big, apparently. Let's make it really big. Okay, so the first thing they want us to do is to find DF. Zelda. All right. We want to find DF. Okay, and we know that DF is the mid segment of ABC. So, and they also tell us that BC down here is 90 inches. So, since DF is the mid segment and BC is 90 inches, how long would DF be? It's half of 90, right? Because our theorem 5.1 says the mid segment is half as long as the third side. So this is just 45 degrees, or 45 degrees. 45 inches. I've been doing too many angles. 45 inches. Okay. Color code, another, well, we got to do red and green for Christmas, right? All right. EF is also the mid segment of ABC. So EF is the mid segment of AB. And hey, we need to find the length of AB. Well, EF is 45 inches. So how long would AB be? The middle point is 45. So the outer edge would be double that, 90 inches. Voila. Easy. We like easy, right? Okay, let's unchristmify this a little bit because the next question's slightly more tricky, but still not hard. Okay, in this example, let's consider triangle ADF. Let's consider it. Consider it triangle. There we go. What is the length of the mid segment opposite DF? Okay, so up here we have established that DF is 45 inches, right? This mid segment opposite DF would be the segment, okay, right, that would go like right along here, right? This would be the mid segment. So what would this blue mid segment be if DF is 45? Anybody? How about half of 45? There we go. Half of 45. So this mid segment would be 1/2 of 45, which is 22.5 inches. Easy, hard? Anybody still here? All right, let's keep trucking. I think this is not too hard. You guys are smart. You got it. Not hard. All right. Good. Yeah, it's beeping at me. All right, so let's try a little bit. This is like the tricky example, right? If you got this, you have the homework is easy peasy. Okay. In the diagram at the right, QS equals SP. Okay. So they're saying that QS equals SP. So that's another way to say that they're congruent, right? And that also means that S is the middle of Q and P. All right. So that is, we got that all from QS equals SP. PT equals TR. PT, oh, I wanted a different color. Hold on. PT equals TR. So that means that those PT and TR are congruent, and this point T is also the midpoint. Okay. We want to show that the endpoint is we want to show that QR is parallel to ST. We want to show that these two are parallel to each other. Okay, that's our ultimate goal there. They're messy, so I'm going to erase them a little bit. We want to show that these guys are parallel to each other. Okay. All right. So it's kind of typed out here for us. Let's fill in the blanks. Because QS is equal to SP and PT is equal to TR, S is the, we already talked about this, right? S is the midpoint of QP, and T is the midpoint of PR. We already established that by definition, right? So now, because S is the middle of Q and P, and T is the middle of P and R, this purpley, let's see, it's going to be green now. No, not what I wanted. I don't want a text box. Sorry. What does this make ST right here? ST connects midpoint S and midpoint T. So ST has to be a mid-segment, right? Mid-segment of the triangle. Okay? So if ST is the mid-segment of PQR, then by the theorem, we know that the mid-segment is always parallel to the third side. So we know that QR and ST are parallel because of theorem 5.1, the mid-segment theorem. Cool? Okay. If in the same example, V is the midpoint of QR, okay? So if V is the midpoint of QR, whole nother color here, V is the midpoint of QR, then these two line, then V is the midpoint, and, oh, I even erased my line. SV is also a mid-segment of the triangle. And that also says that SV and PR are parallel to each other. Okay? Pretty easy peasy, right? Easy peasy, lemon squeezy. All right, so I think you guys can tackle 5.1 easy. You'll have no problem with that. We're going to get into 5.2 a little bit. I don't know if we'll finish it or not. If not, we'll just finish it on Monday. Okay? Okay. 5.2, pull out your notes. We got some definitions and some theorems. I know. I need to turn off that thing where it bings at me every time. Okay. You guys ready? Got your notes? Ready to go. Perpendicular bisector. So this is where 5-1, easy peasy. 5-2, slightly more complicated, has a lot of big words, still does not mean it's complicated. Just kind of, we're going to break it down to what it means, all right? So let's think about what the words mean before we even kind of define it. So let's remember, what does perpendicular mean? Okay, so something that is perpendicular, just a reminder off to the side here. Okay, perpendicular is indicated by this symbol, right? I'm not going to write, it's going to take me forever. Perpendicular, okay? Basically, if one line is perpendicular to another line, that means that where they intersect is at 90 degrees. Okay, or if, yeah, I mean, that's the basic definition. Where the two lines intersect, we get 90 degrees. So we have perpendicular, that's our first word. And the second word that we have is bisector. Bisector. Okay. So a bisector just basically means that we're going to bisect. So we're going to divide a segment into two parts. Okay. Sorry, hold on just a second. In addition, the bisector means that it's two equal points. It's kind of like a midpoint, right? So then if we put the two words together, a perpendicular bisector. So, well, let me just take a step back. The difference between a bisector and a midpoint, the midpoint is just a point. Okay? So this is a midpoint right here. A bisector is actually when you have the midpoint and then there is a line or a ray or a line segment that goes through it. So the bisector is the technical name for the line or ray that goes through it. So if you're wondering the difference between the two, midpoint is just that point, bisector is the actual line array. So a perpendicular bisector, okay, would be, I have a line, here is my midpoint. Then I have let's do another line that intersects at the midpoint and it's at 90 degrees. Okay, so this would be a perpendicular bisector. All right, if you would like the words for that, type them on here. So a perpendicular bisector is a segment, ray, line, or plane that is perpendicular to a segment at its midpoint. Okay, so does that make sense what that is? It's anything that cuts another line at 90 degrees. basically. All right. Next word, equidistant. Equidistant is basically what means that if you have, let me write the words first. A point is equidistant. I feel like this is so quiet today. If I'm so used to you guys chatting in class, if it's the same distance from each figure. All right, so let's talk about something that's equidistant. All right, so we have a point here. Well, I always do that. I always want to draw that. No, okay. All right, so if I have a square, a perfect square, right? And I draw a point right in the center. That's supposed to be a point right in the center of my square. Okay, then that point is equidistant because it's the same distance from everything in my figure. Equidistance from here, equidistance from here. It's not a perfect example, right? So it's equidistant between this line and this line. It's equidistance between this line and this line. Okay, if I have a triangle, right, and I pick a point here, then it is equidistant from any point on my triangle that I draw out from that point in the center. It's equidistant. Okay. The other two lines come with the next theorem, so we'll wait for a second. So let's kind of, yeah, let's start with perpendicular bisector and equidistant, and then we'll come back to concurrent and point of concurrency in a minute. So all those words so that we can have two more theorems. Hooray, right? Theorem 5.2 and theorem 5.3. Perpendicular bisector theorem and then the converse. So remember, when we have a theorem in the converse, that means that basically the theorems work both ways. So the converse just basically means the opposite. Okay. So in a plane, if a point is on the perpendicular bisector of a segment, then it is, you're all in suspense, then it is equidistant from the endpoints of the segment. So if CP is the perpendicular bisector of AB, then CA equals CB. Okay. In a plane, if a point, for this is 5.3, if in a plane, if a point is equidistant from the endpoints of the segment, then it is on the perpendicular bisector of the segment. So if DA equals DB, then D lies on the perpendicular bisector bisector one of AB up here. All right, so I'm going to give you a second to fill those in your sheets. Actually, no, let me explain them and then I'll give you a second because you want to make sure you draw this picture in here, okay? So first of all, can you see why I just spent like 5 minutes explaining what perpendicular bisector and equidistant means? Because these two theorems basically are the definitions of those words. So we definitely need to understand what they mean so that we can understand what the theorem means. I didn't just want to torture you with vocab, I promise. All right, so let's talk about what they actually mean. And I think they make sense, but that's not what I wanted to do. That's also not what I wanted to do. Okay, well, we're just going to have a box there. Okay, so we have a triangle, right? Draw a nice little triangle there. All right, we have a triangle. The first theorem, 5.2, says, in a plane, if a point is on the perpendicular bisector of a segment. Okay, so what they're talking about is, let's look at the bottom of our triangle down here. Okay, that's not what I want to do. Let's look at the bottom of our triangle. Right down here. Okay, where is the midpoint of the triangle, of this segment of the triangle? The midpoint's right in the middle, right? If we take, this is the midpoint right here. If we take that midpoint and we draw a line, let's just say a line, that is straight through the midpoint and at 90 degrees, this line is going to be my perpendicular bisector. Okay, sorry for the crazy writing. But this, you see this nice, I actually made it straight right through there. This is the perpendicular bisector. Okay, so if the point is on the perpendicular bisector of the segment, then it is equidistant from the endpoints of the segment. So what they're saying is that if you draw this perpendicular bisector, then this is one endpoint and this is the other endpoint. Then these are equal distance from each other. So the theorem itself is not hard. It's like, well, duh, if I draw a line through the middle, right? If I draw a line through the midpoint and make a bisector, then yeah, what I divide it in half, those two sides are going to be equal. But we just have to have a lot of fancy words to be able to say that they're equal, right? But I think that makes sense, right? You guys still here? All right. I see some thumbs up. And then the opposite is true too. So 5.3 says, basically, in a plane, if a point is equidistant from the endpoints of a segment. So basically 5.3 is saying start with the purpley pink or purpley blue, right? So you know that this point is equidistant from the endpoints. Then it is on the perpendicular bisector. So if this point is equidistant, if purple's true, then green is true. So 5.2 says if green is true, purple's true. And 5.3 says if purple's true, green is true. Okay, so let's actually try an example, okay? Okay, so we got a triangle. Okay, so line AC, let's make it big again. Line AC is the perpendicular bisector of BD. So AC is the perpendicular bisector of BD. Okay, find AD. So they want us to actually find one of these lengths over here. They want us to find AD. Okay. So let's talk about this. In a plane, if a point, sorry, let me start back here. So let's talk about this. We know that AC is a perpendicular bisector. So for sure, the distance between BC and CD is congruent to each other. Okay. We also know from this theory, which I didn't quite point out before, we also know that the endpoints are equidistant as well. So we also know that these two sides are equidistant as well. So we know that AD is equal to AB because of our bisector. Okay, and then we just do some algebra. So AD is equal to 4x, and AB is equal to 7x minus 6. And if we solve for x, we end up that x equals 2. So let me solve for x off to the side here. 4x equals 7x minus 6. And we're going to add 6 to both sides. And we're going to get 4x plus 6 equals 7x. Subtract 4x from both sides. And we get that basically, I'm running out of room, 3x equals 6 or x equals 2. So if I wanted to know how long AD is 4x, which is 4 times 2, which is 8. Okay, so let's do another example because I didn't like that example a whole lot, even though we just did it. It's not my favorite example, so let's do another one. Okay, example number 2, use perpendicular bisectors. In this little kite diagram, KN is the perpendicular bisector of JL. Okay, and that's why you see this little right angle here, because the perpendicular bisector, we know that this and this are congruent. And it says which segment lengths in the diagram are equal. Okay, so we know that JN is equal to NL, right? And that's just our theorem that tells us that it's because that KN is the bisector, we know that JN is equal to NL. Okay? Because of our segment bisector theorem, well, I guess I should do another thing. Just by looking at the picture, what other segments do you know are equal to each other? What about these two that both say 13 on them? Can we say that JK or JM equals LM because they both equal 13? Yeah. I mean, they're both labeled as 13 on there, so we can say that they're equal to each other because they have the same length, right? Okay, and then the last part is that this one isn't exactly as clear, but I don't like it. It's actually not labeled on your paper, so I'm going to have to look at that when we come back. But we also know that JK, right, and KL are also equal to each other because any 2 points are congruent to each other. So we also know that JK and KL are equal to each other. Okay, so we know that basically we have 3 sets of segments that are congruent or equal to each other. The second question is point M on line KN? What do we think? Is point M on line KN? Well, it sure looks like it from the picture, right? But we have to actually be able to prove it. So we know that since if we continue the line on, right, and this line segment and this line segment are equal to each other, if we use the reverse, right, if we use the converse of the segment bisector theorem, we can say that yes, because of theorem 5.3, and we know that JM and LM are equal to each other, that M is on KN. Okay? Make sense? All right, cool. Last one for today, and then I'll send you guys on your way. Got this pretty picture here. Which segment lengths are equal to each other? And they tell us up here in the diagram, JK is the perpendicular bisector of GH. So this is the perpendicular bisector of GH. That's why we get this little thing here. So we know which segments are equal. Well, we know that, and I wrote over top of it, GK is equal to KH. That's these guys down along the bottom. These two are equal to each other, right? We also know just from looking at the picture that GF is equal to HF. And because of the perpendicular bisector theorem, we know that GJ is equal to HJ. GJ is equal to HJ. Okay. And then we want to be able to find the length of GH. So GH is the line that goes from here to here that I wrote all over top of. Okay. But we also know that GK is equal to GH. So we could say GK equals KH. GK is 2x and KH is x plus 1. So we saw that we get that x equals 1. So that means that this is a length of 2 and this is a length of 2. So GH is going to be 4 units long. Okay. So that's fun with perpendicular bisectors. We'll do, on Monday in class, we'll do a little more review. We'll go over a few more examples, and we'll finish up with theorem 5.4, and go keep chucking along through chapter 5. Okay? Sound good? Awesome. I hope you guys have a great day. Thanks for coming, and I will see you on Monday. Have a good weekend. Bye, guys.